So we'll talk more about inductors and transformers and then piezoelectric devices called crystals. So what are inductors? They're just coils of wire that create a magnetic field because as you send current through a wire, you get a magnetic field that's around the conductor and perpendicular to the current flow. So you use the right-hand rule. If you coil it up, then those magnetic fields align themselves. So you increase the magnetic field more on the inside than on the outside. If you put some material in the middle that has higher permeability than air, then you can increase the amount of, or the flux density that's inside that coil. And we do that by using powdered iron or ferrite, or in the case of power transformers, it's just some special kind of like silicon steel. And the whole purpose of it is to increase the amount of inductance you can get out of that coil. The powdered iron is, I guess, used to see that normally in older radios where the IF transformers had a little tuning slug, which was a powdered iron slug that you could screw up and down. And depending on how deep it went, it would increase the inductance or bring it up, it would reduce it. Ferrite you normally see in toroids nowadays, and most of the fixed inductors tend to be either powdered iron or ferrite. Ferrite gives you much higher permeability and higher inductance rating. However, not quite as high a frequency range. And they tend to be more lossy. So a lot of times they're used as suppression devices where you put a ferrite bead or toroid around a conductor or a coax in order to reduce the amount of current flow on that. In the case of a coax, you put it on there instead of the outside of that shield just looking like a straight conductor. If with a toroid, a ferrite around it, it becomes an inductor, so it tends to block current at higher frequencies. And once again, I learned last week, if you operate an inductor above its resonant frequency, because it's going to have parasitic capacitance, so it's going to be a parallel tuned circuit, it starts to look like a capacitor instead of an inductor. And the reason for using something like a ferrite or powdered iron core, particularly a toroid, is that you maintain the magnetic field almost entirely within the coil itself. So you can have them adjacent to one another and there's not much mutual interaction. If those were air core, then you'd have to be very careful, put them at right angles, things like that. If it's just a straight coil, cylindrical, we call that a solenoid. Whereas if it's on a toroid or a donut-shaped device, we call it a toroidal inductor. The core materials can also be, I learned recently, phenolic. I'm in the process of building some bandpass filters, and it turns out that a lot of them with the zero mix, instead of being powdered iron, it's actually phenolic. So it has the same permeability as air. Main thing on toroids that they are a little more compact. They don't take up, they're more efficient space-wise. So they're better for small, when you're trying to make a very compact system. And the permeability directly affects the inductance. So the higher the permeability, the higher the inductance. But it's a formula that not only includes the permeability, but the area of the coil itself and the number of turns. So the more turns you have, the larger the winding is, and the permeability all affect what the end result is in inductance. There's just a picture of a toroid and how the flux lines are all contained within, and formula there for figuring the H field. And another one over there for the actual inductance, and you can see the number of turns squared times the area times the permeability divided by 2 pi r.
2 pi r of what? Of the toroid, of the core, or the what?
The wire. Which is why I think that is a factor in trying to figure out why, if you increase the size of the conductor, how it affects its electrical length. Because if you look at that formula and you look at the formula for capacitance, where you've got the outside due to skin effect, you've only got the outside of the conductor. It appears that increases at a higher rate than the inductance does.
It looks like on this drawing, they've labeled R. They've labeled R to the center of the core for the toroid itself.
Yeah, the little one.
Yeah.
Oh, that does.
But that.
Oh, yeah, there it is on the back. Yeah, it's in the back. I didn't see that. That's a good point.
But then why do we have the area?
2 times pi times r would be the circumference of the toroid. The A would be the area, I guess the cross-sectional area of the toroid.
Yeah,
I'm not sure exactly what the A would be.
Yeah, the A is the area within the coil itself. So it's going to be the
area of the cross-section of a part
circumference of the toroid times the diameter of it, the winding itself. So as those winding gets larger, your inductance increases, regardless of the diameter of the toroid. Of course, obviously, there's a limit to how big they can be for a given toroid.
What's A?
A is the area.
Area
of the coil. And there's one turn, you've got a circle, the area of that circle. And as you increase that, the inductance increases. Well, think of it, on your before they started doing toroid chokes for your antenna, you coiled up what, 5-6 turns of coax? Yeah. And the bigger that coil, the more inductance it had. Right?
never did it, so I'm not sure.
Oh, okay. Well, on your Cushcraft out there, I think it has, unless somebody replaced them, it normally comes with 3 or 4 turns of coax as the feed, as a choke.
I'm not meaning to deviate too
Okay.
much here, but we had Clyde did a class
Right.
about common mode chokes.
Right. That's what we're talking about.
Okay. And he said those coils of wire were almost useless. almost.
Well, they obviously- You're going to need a lot of large diameter, a lot of turns in order to come up to the equivalent of having a toroid with multiple turns.
Yeah.
I wouldn't say it's useless, but it's not going to be nearly as much inductance.
Well, what he said, he usually had like 6 turns, 5 or 6 turns of the coax.
Uh-huh.
And he said compared to the toroids, those turns were virtually useless.
It also depends on your frequency range. The higher the frequency, the more those 6 turns have an effect.
Yeah, you probably got that. So, okay, sorry.
No, that's fine. We're here to learn stuff, right? I make my chokes with ferrite beads, 7 beads in a row. It's a lot easier.
Any
With
intent
the-
transmission line?
With the coax wrapped around.
No, straight
Just-
through.
Okay, no.
Yeah. Get a lot of inductance. Of course, it costs more than doing it Clyde's way.
Yeah, I think his was like $20 or something. I missed that class, but.
Yeah.
he-
Well,
The way I do it, it's probably close to 35 or 40 bucks.
the beads that you're talking, that you have, if you took the coax, you're starting here and you loop around one bead and then you loop around another bead, would that change what you're trying to achieve?
No, unless you had more than one turn on the bead. If you only got one turn, the loop doesn't, it's only what goes through the inside of the toroid or the bead. You don't count turns on the outside, you only count the inside. Every time you go through it, it's another turn.
When you go through it twice.
If you went through it twice, then that's 2 turns.
Come down.
Right.
And go back.
But the beads I use are 1/2 inch inside diameter, so they just fit on the coax. Yeah.
Alright.
Okay, so what's the primary advantage of using a toroidal core instead of a solenoid in an inductor? Sounds good. What core material property determines the inductance of an inductor?
No.
It's that little mu sign, I think. Permeability. What happens when an inductor is operated above its self-resonant frequency? We did that last week. I guess if you got it maybe high enough.
Yeah, exactly.
Okay, so we talked about the core material. You can have powdered iron. One advantage of powdered iron is it's not as sensitive to temperature. Ferrite is. If you get ferrites above their Curie temperature, they lose their permeability. And depending on how far you go above, it may be permanent. So you can kill a toroid, a ferrite toroid. That's why if you do, chokes and stuff, well, particularly matching transformers, and you're sending 1.5 kilowatts through it, you got to ensure that you have enough core material to handle the flux, because it heats up. So if basically it isn't a big enough toroid, you're going to overheat it and it's no longer going to work. One reason to use the ferrites is you get a lot more inductance because of much higher permeability, but you do have the temperature issue. The ferrite beads, which is just typically a smaller toroid, you'll see those on a lot of leads, power leads, things like that to get rid of parasitic. See it a lot in the VHF, UHF radios internally. In fact, you can buy a assortment from Palomar of different size clamp-on beads. I think Amazon sells Chinese versions, but probably better off with the Palomars. And you can put them on virtually every cable that you've got in the shack. And more is better than not enough. See, powdered iron, like I said, they're lower inductance, but they're typically allow you to operate at much higher frequencies. When you get to very low inductance and very high frequencies, you typically go back to just an air core because you're only looking at a few turns. The mixes for powdered iron, and as far as I know, the only real manufacturer is Micrometals, and they label them as a T, like a 37 would be 37 or 0.37 inches in diameter. So the XX is the size of it. And then the numbers behind it are the mix. So they have like 10 mixes, where 0 is actually not powdered iron, it's phenolic. I learned that the hard way. And 10 has the most inductance or permeability, I should say. You can find them in rods or beads. They sell surface mount ferrite beads. I don't remember if they're powdered iron or ferrite. It looks like a small surface mount resistor, but it's actually a little bead. And they operate at much higher temperatures. In ferrites, you get much higher permeability. There's typically about 6 mixes. These are mostly made by Ferrite Corporation. And 31 is probably the most popular. It covers basically the HF frequency range. 43 goes a little bit higher. I'm not that familiar with some of the others, but they're more specialized frequency ranges. And so that mix is what those numbers represent. And it's a mixture of different types of oxides to come up with those characteristics. And like we were talking about common mode chokes, that's one of the big uses of it, where whether it's a toroid or a bead, you can do it either way. Just an example of what common mode effect is. In a coax, you actually have 3 conductors. You got the center conductor, you got the inside of the shield, and you got the outside of the shield. Because due to the skin effect, you got current on the inside and current on the outside, basically no current through the center of the shield. Because of the charges and the electrostatic field between the inside of the shield and the center conductor, you've got equal and opposite currents flowing. So any common mode current that's different is going to have to travel on the outside of the shield. That's why you put a toroid around it. And because as far as the world's concerned, that coax just looks like a single conductor on the outside. So it's just like putting a bead on a wire, same effect. There's a picture of a lot of the typical clamp-ons you can get, because if you've already got a cable made, it's kind of hard to slip one of these over a connector. That's why they have the split ones, and they work almost as well. This is showing some of the characteristics of the different mixes and what they're made out of, the frequency ranges. 31s are typically, because they have, I think, a little higher loss, I guess. You normally see those as suppression elements like chokes, or for some transformers in that HF range. So what's an advantage of using a ferrite core toroidal inductor?
Delta, delta.
Did I hear a delta? How does a ferrite bead or core reduce common mode RF current on the shield of a coaxial cable?
Is that alpha?
Well, Sherrod said alpha.
Or then it's out. I think it's out. Yeah, I was thinking off of myself.
I think it's alpha too.
Okay.
Remember, all you're doing is creating an inductor which has impedance at higher frequencies, right? The fact that it's reactive in this case doesn't matter. You don't care what the phase is. You just want to block the current flow. What determines the performance of a ferrite core at different frequencies? Remember the chart?
Jeeves and Charlie.
The type of mix. Which of the following materials has the highest temperature stability of its magnetic characteristics? How do ferrite and powdered iron compare for use in an inductor core? Charlie, what devices are commonly used as VHF and UHF parasitic suppressors at the input and output terminals of a transistor HF amplifier? And like I mentioned before, you have to watch for core saturation, where your flux density is exceeding the capability of the core material itself. And one of the things they list in the sort of data sheet is that flux density. And basically, if you're saturating, it means you've exceeded the ability to store any more magnetic energy. So as the current increases, you're creating a magnetic field. So you're storing that magnetic field in that material. It can only store so much flux, basically. So at a certain point, when you reach that, it stops increasing as acting like an inductor, and it stops storing energy. So like, particularly in the case of a transformer, you're no longer going to have an increasing field. So the secondary is not going to see a changing magnetic field. So you're not going to get the power transfer.
So does that magnetic field get discharged when you're not changing anything? Because you have to eventually get rid of that.
The magnetic field is a function of the current increasing and decreasing. Increasing current increases the magnetic field.
Right.
Decreasing current decreases the magnetic field.
Thinking if you had it on your transmission line. It's getting charged when you key up and then you unkey, it's getting discharged. The magnetic.
Well, it's gonna go on the cycle of the waveform. The
Okay.
positive increase, well, the first 90 degrees is increasing current. And then it's decreasing, and then it increases negatively. So you get a reverse magnetic field, but it stores both.
Oh, so you're constantly flipping it back and forth.
Right.
Okay.
And this is typically what you would see on the output when everything's fine. As you start approaching saturation, I'm not sure I believe they're all nice little square things, but I didn't create this chart. And as you get higher and higher in the saturation, then you start getting really weird looking waveforms on the output. So what is inductor saturation? Remember, magnetic flux is the equivalent of current. It's like magnetic current. Oh. Come on. I mentioned variable inductors, and usually you have some way of moving a slug of material in and out of a coil. Normally, it's an air core inductor, and then you're injecting some other material. Actually, could be brass, where brass has a lower permeability than air, so you're really going to decrease it. And in fact, one of the tricks when you're trying to tune like filters, you got multiple coils. You can make, or they sell these little sticks where you've got a piece of ferrite or iron on one end and a piece of brass on the other end, and you can kind of stick one end or the other in the coil and see how it changes to see whether you need to increase or decrease, because you look at the overall pattern, see whether you need to increase or decrease it. It's a whole lot easier than trying to disconnect it, take a turn off, put a turn on, resolder it.
My dad made one of those tools. I don't know if it's still around, but yeah, you had to stick with the rod.
Yeah. So which type of core material decreases inductance when inserted into a coil? Brass. I'm not sure what aluminum would do, but apparently.
They should have arranged those different. They should have had A for aluminum, B for brass.
Well, it could wind up that way on the exam,
Oh,
because just the way these show up in the question pool isn't the way they show up in the exam booklet. They rearrange the answers to fit the template. So you can use a common template for a lot of different exam booklets. In fact, Gary was telling me he has his custom made. Yeah, he sends them the basically his template, the way he wants it laid out. And they adjust the answers in the booklets so he can use Gary Lidgren. Yeah. Well, he told me. I don't think he'd lie.
he designs his own test.
No, the template. We use templates, whole colored transparencies with holes to match, right?
The grading template.
Grading template.
Yeah.
Yeah, this is when I remember seeing him using them out there.
So you get 4 booklets out of one template. You turn it over, you turn it up.
Oh, takes a lot of thought.
That's why the order of the answers changes. So you can't memorize the fact that the answer to this is B. It's probably not going to be B on an exam.
Yeah, but I was talking about
I understand. I understand. Okay, transformers, it's just two inductors that are closely coupled. You could have an air core transformer. I don't know that I've seen one, but theoretically you could. Usually there's some higher permeability material that the 2 or 3 or 4 coils are wrapped around, so that they have a common magnetic field and common lines of flux. So when you change the magnetic field on what's called the primary, which is arbitrary, it induces a current in the second. Well, actually, it creates a voltage potential, which can create a current. Obviously, if it's not connected to anything, there's no current flowing. So it needs some sort of path. And the voltage that you get on the quote secondary is going to be based on the turns ratio between the primary, what you're calling the primary, and the secondary. So if you have more turns on the secondary, you're going to increase the voltage, but you're also going to decrease the current because the power out cannot exceed the power in. And if you're using it as an impedance matching transformer, then the impedance ratio is the square of the turns ratio. So if you have nothing connected to the transformer on the secondary and you apply a voltage on the primary, you're going to get a current flow, which is called the magnetizing current. So it's going to create a magnetic field within that transformer, even though there's no current flowing on the secondary. So that's kind of a lossy thing in the transformer. You've got to account for the magnetization current as well as the power you're going to transfer. If you, like I said, if you're using the transformer as an impedance match, obviously you got to make sure you're not saturating the core again, because you're going to get those weird effects, which also creates third and fifth and other order harmonics, probably mostly third order. And if you look at the equation down there, the fundamental frequency is going to be reduced down to like 3/4, and the rest of that power is going to be generating a third harmonic. Omega.
Oh,
2 pi f.
lower.
The lowercase omega. And this is a plot of what the input and output kind of looks like. So
They're still in phase, right?
they're still in phase, but it's not exactly the same waveform. So what's the current that flows in the primary winding of a transformer when there's no load on the secondary? Delta. Okay, so if it's a power transformer, we typically use iron. It's some kind of special silicon steel that they normally use. And it's built up of laminations there's some sort of a coating on those laminations. So it's actually an insulator. So you've got all these separate little fairly thin pieces that make up that core. And that's to reduce the eddy current. If you had just one block of iron, then you're going to get, because of the magnetic field, it's going to also create a current flow because it's a conductor. So you got a changing magnetic field around the conductor, it creates a current or a voltage, which can create a current. In order to reduce that large eddy current, if you divide it up into these very small pieces, then you have very small eddy currents in each one of those little laminations, and they don't really add up together. So there's a lot of transformer loss due to the eddy currents. So that's why they do that, is to make the transformer more efficient. Because you're going to lose power because it's going to heat up the core with that eddy current flowing in there.
Why do they put them in oil for power transformers?
The heat,
So the oil just all it does is cool it?
yeah. And it's designed, if you notice, they have those pipes, okay?
Yeah.
It's set up so that the heat actually causes it to convect and circulate.
So it circulates.
And you got fins on the pipes.
Oh, the-
That's something on the AC fan.
There's a lot of power in those big transformers.
Yeah.
And this just shows the difference between whether it was solid or laminated. You can see all the small eddies. You still got them, but they're much smaller and isolated.
So they don't add up to the ones on the right don't add up to equal the ones on the left in this.
That's the theory. I don't know for sure, but that's what they all say. And they are always right.
They all have to be.
That's what they say. That's what they say.
But because there's insulation there, that eddy current itself is going to create a magnetic field. But I think there's enough isolation that it's obviously reduced. That's why, or else they wouldn't be doing it, because it costs more to make them that way. Why are cores of inductors and transformers sometimes constructed of thin layers? Okay, piezoelectric devices. Piezoelectric crystals are still used. Used to be to control the frequency of your main oscillator. Old stuff had plug-in crystals on the front, and you had to, depending on what band you wanted, you had to plug in the right crystal. Then they started, when they became cheap, they realized they could make filters by hooking a bunch of crystals together in a lattice formation at different frequencies, and you could make a very sharp cutoff bandpass filter. And they did that until recently, where with SDR radios, you can make a better filter in software. And the important thing, exam-wise, is to know what the equivalent circuit of a quartz crystal actually is. So it's defined as a motional capacitance and loss resistance in series in parallel with a shunt capacitor that represents the plates. Because when you make a crystal for an oscillator, it's a piece of quartz, and it has plating on it to make connections to it. That's where you apply the voltage, and the voltage causes that quartz to flex, and it'll have a resonant frequency depending on its thickness, the way they cut it relative to the crystal itself. So they machine those down to get, and it's mechanically done so it's resonant at a fixed frequency. And it's a mechanical resonance that's induced by applying a current, or a voltage, I should say. When you bend it, it generates a voltage. I don't know how that works. It's the piezoelectric effect.
Really old if you had to grind your own frequency because.
I've heard about that. Did you do that?
I use Ajax,
Really?
but Ajax on a plate, take the crystal out and just rub it around like that, clean it, put it back in the crystal and put it in the radio and see what you got. I use quartz.
That raised it, right?
Yes.
What'd you do if you wanted to lower it?
Get another crystal.
Don't break.
Yeah.
We used to complain that them damn crystals were $3 a piece.
Oh, yeah.
I still got a whole slug.
That was a lot of money though.
Oh, yeah.
Why not a 10?
Yeah. I remember buying my first transistor, CK722. I saved up my money. It was like $6 or $7. Little blue.
The only transistor existed.
That was in a little metal can.
Yeah.
Yeah.
Little blue metal can by Raytheon. I think it was. All right, there's the equivalent circuit. So we have this quartz crystal and the metal plates. Now, what did you abrade
Did what?
when you rubbed your crystal? What part?
The quartz part. See the two plates?
Yeah,
The crystal was physically in between those two plates.
right. So you did an edge or something?
And then you take the plates off and you got.
Oh, I never took one apart. I actually just,
Yeah, you get a little sliver.
it's just a mechanical connection? Oh, I didn't know that.
Well, the big one, yeah, there's little screws and you take it apart. There's the other plates and like when there are little springs in there.
Yeah.
Yeah.
That's
Okay,
why
well,
You could bang them like that with your finger and it changes the frequency.
The military had big ones. I don't know if you've ever seen them. They were about this wide, about that high,
Oh, yeah.
two big ones. I still have one of those too.
It had this 100 kilohertz, standard for you to have was a big one that
Yeah.
you use at the 0 beat radio. The frequency standard.
Now-
WWV.
now their surface mount's about that big.
Oh,
Yeah.
Well, they.
Temperature compensated.
Stable, then your crystal was in and up. And it
Yeah.
maintained a precise
Yeah.
temperature.
Right.
Motorola two-way radio said.
And you didn't take the cover off the radio because it would change the frequency
Yeah.
or put it in a draft. So you have a effective series resistance and a series LC circuit. And then the plates themselves act as a stray capacitor. So that's why that long definition, that's what that's representing. Is the motional capacitance and that inductance and capacitance is the electrical equivalent of that mechanical resonance, the mass of it and the springiness of it. The springiness part is the capacitance and the mass is the inductance. So- Huh?
I mean, that's what crystal microphones and all that.
What is piezoelectricity? Silence.
Charlie,
Charlie.
Either Alpha or Charlie.
Yeah, that's what I'm thinking, I'm certain.
Well, let's go with Charlie because they don't generate electromagnetic waves.
Oh.
Electricity, that's kind of why I was.
It generates an electrostatic field. Which of the following is an aspect of the piezoelectric effect? Yeah, you can throw Charlie and Delta away.
Yeah, those were.
Yeah.
As far as I know, light doesn't have anything to do with it.
I'll call it Alpha. I think I'll go with Alpha too.
No.
All right. What is the equivalent circuit of a quartz crystal?
Alpha.
Who wants to go with alpha? Two alphas?
Yep.
Bravo,
It's not a-
Charlie? Alpha. Series RLC and a parallel capacitor.
The thing that kind of got me on that was the stray capacitor spark. We didn't talk about stray, it talks about the contacts.
Well, that's
But they all have straight capacitance on the answers.
right. That's part of the stray capacitance.
Wow.
I mean, it's, the plates weren't intended to be a capacitor, they just happened to be conductors separated by an insulating material, so there's an electric field, therefore it can store electrostatic energy, and by definition, that's a capacitor.
Makes.
Okay, so we learned about a little more about inductors and transformers and piezo devices.